Hello everyone. In this video I'm going to explain principal component analysis. So principal component analysis, why we actually use this concept, the reason is we want to reduce the dimension. So this is actually used for dimension reduction. Now let me tell you what is dimension reduction. Let's say we are given some data and I'm considering a very simple data. I'm given a data in a form of x and y. So some value are given for x and some value are given for y. So in this data the number of input variable is 1. Okay, and let's consider we are going to train a linear model on this data. So when we train a linear model for a line, what we need value of two variable. One is known as slope and another is known as intercept. So simply saying, if we are considering linear model, so in that linear model, if we are having one input variable, so in that case, the number of variable for our model will be two, and that model is line. So I'm going to make it simpler. That's why I'm considering line. So in case if I'm having a data set and that data set is having 10 input variable, so if we are going to train a linear model on this data set, we need to find out uh, parameter for our model, and the number of parameters will be 11. So as the number of input variables, or we can say as the number of dimension increases, the number of parameters for the model also increases. So in our case we have considered only a linear model, which is a simple model. So if we start considering other model as well, so the number of parameters also increase. Now when the dimension increase, we can say it will increase model complexity. So how we are going to uh, say that what is model complexity? So we can consider it as a number of parameter we need to find out for our model. So in one attributed data we need two parameter for our model. For 10 we need 11. So as we increase the number of input variable, the number of parameter for our model also will increase. So in simple term we are saying it, this is the model complexity. So number of dimension, okay, number of dimension will increase model complexity. And what is the another problem if we are having a very high dimension data? uh, Let me take this example first. So in this example, if this is a regression problem, it means the type of these values are continuous. So if this is a regression problem, we can plot that data easily. Okay, or we can say we can interpret those data very easily. So if this data is given to us, we can easily see, okay, this is going to follow a linear trend. But in case if we are given this data set 10 input attribute, so it will be highly difficult to understand the interpretation of that data. So for high dimension of data, these are the two problems we are having. So first problem, as the dimension increase, model complexity will increase, and it also will become difficult to understand interpretation of that data. So in order to uh, reduce the dimension, principal component analysis is the first method we are going to study. Now before going to understand principal component analysis, let me show you some basics. Like let's say we are given some input variable x1, x2, x3, x4, and this is the target variable. So what people normally do is they usually calculate this entity. correlation. Correlation actually tells how two variables are related to each other. Let me take this example. If for x1 and x2 correlation value is 0.9, so it means that 90% of the time x1 and x2 variables are relating to each other, or we can say they are similar to each other. Okay, it can be positive, it can be negative. So in case of negative, we can say they are negatively correlated. It means if one will increase, another one will decrease. So normally people, they calculate the correlation between each pair of these variables, and then they will find out set of pair of variables which are highly correlated. So if a correlation is giving you 0.9, 0.95, it means those variables are highly correlated, or they are conveying same information. So in that case we can consider only one of them, it will be sufficient. So one way is this of dimension reduction, we can calculate the correlation. So this correlation actually gives us a matrix. So this matrix will be like this one: x1, x2, x3, x4, and this side also. So this will be a symmetric matrix. Okay, now so people normally compute this matrix, and on the basis of this matrix they will decide, okay, which attribute they need to take for their computation. Okay, so this is the correlation. Now next thing is that uh, let me consider a three-dimension data, and in this three dimension I'm having a point, and this point is actually 3, 4 and 5, or in another word I can say it is 3i, 4j and 5k, if I'm representing this point in a form of vector. So this is the, let's say, value of x. Now if someone asks you what is the uh, value of this vector in the direction of x, or in other word I can say what is the projection of this vector in x direction. So as we know, in x direction the unit vector is 1 0 0, or we can say it is I, sorry, I plus 0 plus 0. Let me write here 1 dot I, 0 dot j and 0 dot k. So if we want to find out the projection of this vector in the direction of x, we can simply perform a dot product between x and this input x, and let's say this is the direction u. Now if we are having these two data in form of matrix, so let's say if we, this is the value of x, a vector, and u, which is the direction, this is the direction. So here if you want to perform a dot product, what we need to take, we need to take the transpose of this vector or this matrix, and this will take we as it is, so it can be written as xtu. So now I'm going to start the principal component analysis. So what principal component analysis say, that we are given some data. Okay, now what we have to do, we have to find out a direction. Let's say this is the direction, I'm pointing this direction as u. If we project each of these data on this direction, and this is the, so these are the projected point of these data set. So let's say these are the rest of the data point. So the variance of the data point will be this one. So what PCS says that find out a direction in which if we project all of our data, it will give us maximum variance. Okay, so this is the core concept of PCA. So what we need to do, we need to find out a direction in which if we project all of our data set and if we compute the variance, that variance will be maximum. Okay, so let's say these data are given in a form of x. Okay, and this x is a d-dimensional data, and I'm considering this direction as u. So if I want to find out projection of x on u, what I can write, I have to perform dot product, and that dot product uh, in matrix form can be written as x t u. This is a matrix product and t representing transpose, and I am representing it as a z. It means z is these points. Let's say z1, z2, z3, z4, and so on. So I am representing all of them by z. So this is the projection. Okay. Now we are making here one assumption. What is that assumption? We are saying that we are considering this data as mean centered data. What is the meaning of mean centered data? We are considering they are having mean 0. So all these data point, if we consider their mean, it will be 0. So some of may have might get confused that why we are considering this one, or this is not the situation with all of our data. So what we can do, we can convert our data in a mean centered data by using this formula. So if we subtract mean from each data point, will whatever data point we will get, we will get, mean of those data points will be 0. Okay, so this is our assumption. In case if this is not true, we can convert our data into mean centered data. Now so here these all data points are z1, z2, z3, and so on. Now we want to find out variance of this data, and as we know variance, what is the variance? Variance is actually if we are given some data in form of x1, x2, x3, the variance actually x minus mu 1 upon n summation. Okay, so this is the variance. So we will apply the same formula here, and we will try to compute the variance of z. So here we have considered mean of our data 0. So therefore here I want to compute the mean of z. So I can write this mean as in this form. Okay. Now let's put value of zi here. So value of zi here will be okay. So we got this term. Now if we are having some vectors, let's say vector is our x1, x2, x3, and I want to perform x square. What is x square? X square is x1 square, x2 square, x3 square. Okay, so in order to perform x square, which is equivalent to this one, what I can do, I can sorry, I can multiply x1, x2, x3, this matrix with this matrix. So it will give you the same term. So in another word, I can say if I want to compute the square and if x is in the form of matrix, so I can write it as a x transpose x. Okay, let me take another page. So the quantity we got, that quantity was 1 upon n I z I square. Then we put here our value, and square in matrix form can be written as xi transpose u, transpose, and then this one is the simple term. Now, if we take this transpose inside, what we will get is we will get u transpose xi. So transpose of transpose will be the original matrix, and when we take a transpose inside, the order of the inner matrix will be reversed, and this is our rest of the part. So here I can write this one. This is the transpose u, and let me take this summation inside. As you can see, these u are not having any I. Okay, the only changing part is this one. So I can write this as, okay. Now what is this entity? Okay, so let's see if we are given some xi, and this xi is x1, x2, x3, and if we perform xi multiply with xit, so we are performing product of these two. So if we perform a product of these two, what we will get? We will get a 3 by 3 matrix, and this is the summation of all of those matrix and divided by n. Okay, so this is actually a covariance matrix. Okay, and covariance matrix we can denote with summation sign. So what the term we got this one, variance of z is equal to ut covariance matrix and u. Okay, we got this is the variance after projection. Now what is the core concept of PCA? PCA core concept is we want to maximize this variance. So we want to maximize this variance. Okay, now the thing is that these u, t and u, these are directions. Okay, and we will put one more constraint that u is the unit vector. So if u is a unit vector, in another term we can say u square will be 1, and in matrix form we know what is u square. U square is ut u equal to 1. So now what we are going to do, we are going to combine this expression and this expression into a single problem, and here this can be done by using Lagrange. So this problem can be written as a Lagrange problem. So the final expression we will get, the final expression will be something like this way. Okay, this is the expression, final expression. So let's say this expression is given to you, and the person is asking you have to find out value of u that maximize this final expression. So here we will use maxima. Uh, we will consider it as a maxima problem. So how we used to solve these kind of problem, we will find out the derivative, partial derivative of this expression with respect to u. So let's say if I'm denoting this as a w, it will be dw1 du. So we are going to perform the derivation, differentiation. Sorry, I'm sorry, I used the derivation. So we are going to differentiate this term. So first, we will perform differentiation on this term. So this is actually u square. Okay, we will consider for simplicity at a u square, and if we perform the differentiation with respect to u, what we will get? We will get 2u. So I'm going to write it as a this manner. Here what we will get, this also will be considered as u square, and if we perform the differentiation we will get to u, and this will be 0. So we have find out the differentiation of this term. Now we will put it equal to 0, and then we try to find out the value of u. Okay, so from this expression what we actually get, uh, I'm sorry for one correction here, this is actually a negative. I'm really sorry for that. So what we actually get is, we get this term. Now here, this is a covariance matrix. This is the unit vector or direction. This is some constant, and this is the same vector again, the same unit vector. So if you can think of this expression, you might have seen this expression somewhere. So it is actually a eigenvector. Okay, so u is actually a eigenvector, and lambda is here eigen value, and this is a very important term. Now what we will do here, we know that variance of z is due to, now from here we know that the multiplication of these two terms equal to lambda and u, and this become u to u, and as we know u is a unit vector, and this term is equivalent to u square, which is 1. So variance of z, what is this one? This is actually a eigenvalue. So what PCA want? PCA want that you need to find u such a way that it give maximum variance. Okay, and from here we know that variance of z is equal to eigenvalue. So if we want to find out the maximum variance, that will be the highest eigenvalue of the covariance matrix. So the direction, how we can find out the direction? So direction we can find out by finding out the eigenvector of the covariance matrix. So it can be written as, find out eigenvector of covariance matrix. That's it. Okay. So now, so if we want to reduce our d-dimension data to one dimension, what we can do, we can perform, we can find out the eigenvector of covariance matrix, and we will select the eigenvector which will have maximum value of eigenvalue. Okay, which will be having maximum eigenvalue, that will be the direction we are going to use for our dimensionality reduction. In case if we want to reduce a d-dimensional data to k dimensional, so we can find out k eigenvector in such a way their eigenvalue will be higher than the rest of eigenvalues. So this is the principal component analysis. Thank you very much for watching.